Hi students, today we are going to start a new chapter in our paper Nanoscience and Nanotechnology, which is the Characterization Tools of Nanomaterials. The characterization refers to the study of material features such as its composition, structure, and various properties like its physical properties, electrical properties, magnetic properties, optical and thermal properties, etc. So, you synthesize a material and we try to study the features of the material synthesized by us. Okay, so suppose you are synthesizing a nanomaterial by one of the methods that we had discussed in our last classes. That is, we had discussed about different kinds of synthesis methods like sol gel method, electrodeposition, molecular beam epitaxy, physical vapor deposition method, chemical vapor deposition methods, a number of methods like sputtering, etc., whereby we can synthesize nanomaterials, especially thin films. Next, here we are discussing the characterization tools for studying the features of such synthesized materials. Features means we study about its morphology, its composition, and various properties like its electrical property, magnetic property, thermal properties, optical properties, etc. So, in this chapter, today we are going to discuss about a characterization tool which is used to study the surface structure of the nanomaterials. That is, how is the surface morphology of the nano material. Okay. So the surface structure of nanomaterials are studied using various equipments and techniques, and two of the most important equipments used for nanomaterial surface characterization, that is to study about the surface structure of the nanomaterials or to image the surface topology of the nanomaterial, is the two most equipments used for this purpose are STM, that is scanning tunneling microscope, and AFM, that is atomic force microscope. Okay, so we are going to study about imaging the surface topology of the synthesized nanomaterials. How is the surface structure? എങ്ങനെയാണ് നമ്മൾ ഉണ്ടാക്കിയ നാനോമെറ്റീരിയൽസിൻ്റെ സർഫസ് സ്ട്രക്ചർ എങ്ങനെയാണെന്ന് പഠിക്കാൻ ഉപയോഗിക്കുന്ന രണ്ട് എക്യുപ്മെൻറ്റ്സ് ആണ് STM ആൻഡ് AFM, സ്കാനിങ് ടണലിംഗ് മൈക്രോസ്കോപ്പ് ആൻഡ് ആറ്റമിക് ഫോഴ്സ് microscope. Now these equipments, that is STM, AFM, and all these come under, all these are based on a general technique called scanning probe microscopy. Okay, so what is the basic principle of a scanning probe microscopy technique? So scanning tunneling microscope, atomic force microscope, all are based on the scanning probe microscopy technique. Now what is the principle of this technique? Okay, so all the techniques are based on the scanning of the surface by means of a probe. Probe means some metallic tip. Using this metallic tip, the surface of our nanomaterial is scanned. Okay, and the interaction between this tip or the probe and the surface is studied. Okay, so in the scanning probe microscopy techniques, we have a probe. A probe means a sharp tip using which the surface of the nanomaterial is scanned, and simultaneously we monitor the interaction between the probe and the surface. By monitoring the interaction between the probe and the surface, you can study how the surface structure is of this nanomaterial. അതായത് ഈ നാനോമെറ്റീരിയലിൻ്റെ സർഫസ് പഠിക്കാൻ നമ്മളൊരു പ്രോബ്, അതായത് ഷാർപ്പ് പോയിൻറ്റഡ് ടിപ്പ് ഇസ് യൂസ്ഡ് ആൻഡ് ഇറ്റ് ഈസ് അലൗഡ് ടു സ്കാൻ ഓൺ ദി സർഫസ് ഓഫ് ആർ നാനോമെറ്റീരിയൽ. അതിനെ നമ്മുടെ നാനോമെറ്റീരിയലിൻ്റെ സർഫസിൽ സ്കാൻ ചെയ്യാൻ അനുവദിക്കുന്നു. അപ്പോൾ ഈ പ്രോബും, അതായത് ഈ ടിപ്പും നമ്മുടെ സർഫസിൻ്റെയും ഇടയിൽ എന്തെങ്കിലും ഒരു തരം ഇൻ്ററാക്ഷൻ ഉണ്ടായിരിക്കും. ദർ വിൽ ബി സം കൈൻഡ് ഓഫ് ഇൻ്ററാക്ഷൻ ബിറ്റ്വീൻ ദി പ്രോബ് ആൻഡ് ദി സർഫസ്, ആൻഡ് by monitoring this interaction we can recognize or study the surface of the synthesized nanomaterial and we can image it. So in STM, the tunneling current between the metallic tip and the conducting substrate, that means which is our material, is measured. Okay, so I told you the probe or the tip is brought near the surface and some kind of interaction between the tip and the probe is measured. In a scanning tunneling microscope, which is our instrument, first instrument. Okay, in scanning tunneling microscope, it is the tunneling current which passes between the tip and the conducting substrate. That is a conducting substrate. If our material is conducting, then the tunneling current that flows between the tip and the material is measured. If the material is non-conducting, then a conducting layer is coated on a material and the tunneling current that flows between the tip and the conducting substrate is measured. Whereas in atomic force microscope, that is the second equipment which is used to determine the surface structure of our nanomaterial, in the atomic force microscope, it is the van der Waals force which exists between the tip and the surface, which may be a short range repulsive force in its contact mode and a large range attractive force in the non-contact mode is measured. In the atomic force microscope, it is the van der Waals force between, I haven't written the force here, I've missed it. It's the van der Waals force between the tip and the surface which is measured, whereas in STM, it is the tunneling current between the metal tip and the conducting substrate that is measured. Okay, so the van der Waals force may be short range repulsive if the tip and the sample are in the contact mode, and it will be in the long range attractive force. It will be a long range attractive force if it is in the non-contact mode, that is the tip and the sample are not in contact. Okay, now for these techniques to provide us with information about the structure, the following conditions have to be met. അതായത് ഈ ടെക്നിക്കുകൾ ഉപയോഗിച്ച്, അതായത് സ്കാനിങ് ടണലിംഗ് മൈക്രോസ്കോപ്പും AFM, if by using these two instruments or equipments which is based on the scanning probe microscopy technique, using these instruments or equipments, if we have to get an information about the surface structure കുറിച്ച് ഈ ഇൻസ്ട്രുമെൻറ്റ്സ് ഉപയോഗിച്ച് നമുക്കൊരു ഇൻഫർമേഷൻ കിട്ടണമെങ്കിൽ what are the conditions that should be maintained or what are the conditions required? The position of the tip with respect to the surface must be accurately controlled within 0.1 angstrom by moving the surface or the tip. So the position of the tip and the surface must be very well controlled. It must be so close within 0.1 angstrom. So we can do this either by moving the tip or by moving the surface. Okay, the position of the tip and the surface must be very well controlled. The second point is the tip must be very sharp. It must be just 1 atom thick at the tip. Okay, the probe tip must be, the tip of your probe must be very, very sharp. That is, it must be just 1 atom thick when it is closest to the surface. So I'll show you a figure of our scanning probe microscopy technique or a scanning tunneling microscope with its metallic probe and the surface. Yeah, so this figure has been taken from the textbook Introduction to Nanoscience and Nanotechnology by K.K. Chadobadhyaya and A.N. Banerjee. This figure has been taken from that, and this shows the atomic arrangement in our probe. Or I'll show you one more figure. The probe is something like this. Yes, here, this is your probe. So this is a thin metallic tip, and this is my substrate. Okay, where we are measuring the interaction between the tip and the substrate. All scanning probe microscopy techniques use the interaction between the tip and the substrate to determine how the surface of my sample is, to study how the surface of my sample is. Okay, if it is the STM, if the instrument used is STM, then the tunneling current is measured. If the instrument that we use to study the surface topology is AFM, then the van der Waals force between the tip and the substrate is measured. Now, for these instruments to function properly and to determine or to generate the image of my surface, or to give information about the image of the surface of the nanomaterial, two conditions must be satisfied. That is, the distance between the tip and the substrate must be accurately controlled within 0.1 angstrom. Within that range, it must be accurately controlled, and the tip must be extremely thin at the lowermost point of the tip, which is very near to your substrate. It must be just about 1 atom thick. Okay, so it should be something like this. If the atomic arrangement in your metallic tip is shown, so the tip must be at only 1 atom thick, and this shows the surface of my sample. Now, using such a metallic tip, we are going to study how the surface is varying, how the surface topology is for the sample. Okay. So let us come back. So we are studying about the characterization tool, and two types of characterization tool for studying the surface topology is the STM and AFM. And now we are going to study the basic working mechanism of the STM, or the basic principle of STM in detail. So STM is used to study the surface structure of nanomaterials. In an STM, there is a sharp metallic tip which is brought very close to the substrate within about 0.1 angstrom, but they do not touch each other. Here, there is the tunneling current flows between the tip and the substrate. Why a tunneling current? Because they are brought very, very close to each other, yet they do not touch each other. So classically, a current should not flow between the tip and the substrate. But quantum mechanically, there is a possibility for a current to flow between the tip and the substrate, and that is this tunneling current. So here a tunneling current flows between the tip and the substrate, whose surface morphology is to be imaged or measured. Now, the tunneling current is a function of the separation between the tip and the substrate. So, the tunneling current varies as the distance or separation between the tip and the substrate varies. Now, imaging of the surface topology is carried out in two ways. One is the constant height mode. That is, you keep the separation between the tip and the substrate a constant. The separation between the tip and the substrate is kept a constant everywhere. It's kept continuously at a constant, and the tunneling current is measured in each case. So, here every time the tip is kept at a constant position, so that it is kept at a constant height. The metallic tip is kept at a constant height, and in each case the tunneling current is measured. Because the separation is varying here, the tunneling current will vary, and it will help you in determining the surface morphology. Whereas in the second case, the constant current mode, the tunneling current is kept a constant, and the tip is scanned over the surface. That is, the separation between the tip and the surface changes depending on the surface morphology, so that the current is kept a constant. I hope you have understood. That is, in the first case, in the constant height mode that is shown in the figure here, the height is kept a constant everywhere. But as the surface morphology or topology changes, as the surface topology changes, what happens? The current flowing through the separation between the tip and the substrate will vary. The separation here and at this point is not the same as the separation here. As the tip moves to this point, the separation here is different. So the tunneling current will also vary. Okay, the tip is kept at a constant height, that is a constant height mode. Whereas in the constant current mode, the tunneling current is maintained a constant, but in order to maintain the tunneling current a constant, what will happen? The tip will move, or the separation between the tip and the substrate will change, and the image of the surface is obtained. So normally, what mode is used? Normally for the characterization of materials, the mode that is used is the constant current mode. Okay, that is, you maintain the current constant and the height or the separation between the probe tip and the surface will vary. Here the current is maintained a constant by adjusting the tip's height according to a variation in the separation between the tip and the surface. The tip will move slightly up as it passes over the surface atom and moves in. It will move down, or it moves in as it passes over a hollow. Hollow means a depression. So it moves up as it passes over a uphill or over the surface atoms, and it will move down when it reaches a depression, so that in every case the tunneling current is maintained a constant. So I hope this session is clear to all of you. Here we discussed about the characterization. What are the characterization tools which are used to characterize our nanomaterials? Characterize means we study the material features of the synthesized sample, such as its composition, its surface topology, its structure, physical, optical, electrical, etc. properties. And the surface structure of material, or the surface topology, how does its surface structure vary, is studied using two equipments, STM and AFM, scanning tunneling microscope and atomic force microscope. Both of them are based on one common technique, that is scanning probe microscopy technique. According to scanning probe microscopy technique, there is a probe or a tip which moves over a surface, and by monitoring the interaction between this probe and the surface, the interaction between them may be a current flow, or it may be a particular kind of force. Whatever be the interaction between the probe and the surface, that is monitored or measured, and the surface topology is studied. Now, in a scanning tunneling microscope, it is the tunneling current between the tip and the substrate that is measured, whereas in AFM, it is the van der Waals force between the tip and the surface that is measured. Now, for these instruments to work properly, two conditions must be maintained. One is the position of the tip with respect to the surface must be accurately controlled, and the tip must be sharp. Then we learned in detail the basic principle of working principle of STM, that is, either it can work in the constant height mode, where the height of the tip is maintained a constant, whereas the tunneling current varies as the surface topology varies. And in the second case, the current is maintained a constant, and the height of the tip varies, so that we can image out the surface structure or the surface topology. Normally this mode, that is the constant current mode, is used. Now the tip will slightly move downwards when it reaches a depression, and it will move upward when it reaches a height on the surface of your substrate. Okay. In this way, the current is maintained a constant, though the tip is allowed to move up and down according to the variation in the surface structure of your sample. So I hope this session is clear to all of you. If you have any doubt, please do contact. Thank you.